All right, how's it going today?
Good, how about you?
Pretty good. So, the forecast says no precipitation of any kind until at least tomorrow afternoon. So if that holds, we should be in good shape. So, hopefully. So any questions before we continue talking about trees and tree operations? No questions for the exam? The exam is not covering trees. Concepts about hashes and queues and stacks, but no code. Or PA3 questions?
On the exam, will you be asking the values stack and queue or just index of those?
Don't know. Does it make a difference?
Yeah. It takes the extra one step to find the value.
Yeah, but you can do the extra one step, right? Right, as long as you know the concept, right? If you have an array implementation of a stack, you have something that tells you where the top of the stack is, that moves one way when you push, moves another way when you pop. And the value is in the array, right? It's the thing that's pointed to by that variable. Yes. Mm-hmm. So are we doing a stack with an array or with a linked list here? Linked list. So if you've got a linked list, right, and assuming we have a sentinel, so suppose you push 2 and you push 10. So your stack would look like this. Okay, sentinel points to the first node, which is a 10. Next node is a 2. So you want to pop or push? You want to pop. So if you want to pop, basically sentinel next equals sentinel next next. Your goal is to take the sentinel and point past that first node. Effectively delete this from the list. But before you free it off to memory, before you get rid of it completely, remember what the value is, which is a 10, right? So that when you call pop, it'll return a 10. But it's really just a delete the first node in the list operation. Yeah? It's unlikely, but it doesn't hurt to check. It's one line of code, but what you should do if you run out of memory, I have no idea. You could return null, or you could just throw up an error message right then and say help and exit. I mean, it's not going to happen, but it's not bad to see a one if statement when you call malloc. Yeah.
Anything on header files?
Header files? No.
No.
You got questions about them?
No, I was just saying, like, are we gonna have to know like the difference between the pointy brackets versus the quotey brackets? Or?
No, but do you know the difference? Okay. So I can put that question just on your test.
You can put on mine too.
Okay. We'll have 2 versions of the test. All right. Did that answer your question about popping?
Yeah.
Okay. All right. Well, let's insert into trees. Right, so there's an arbitrary binary tree, and we looked at this yesterday. If we want to insert a 95, for example, we start at the root. 95's got to go to the right. Look at this, there's an 80, it's got to go to the right of that. There's a 90, it's got to go to the right of that. There's a 100, it's got to go to the left of that. There's nothing to the left, so that's where we insert. So this isn't bad to write a loop for, right? So insert tree and num. If our number is bigger than the tree's data, this is pseudocode, so I'm just using dots. If the number is bigger than the tree's data, then set tree equal to tree right, and go back up to the top. If the number is less than t data, and there's really no choice, if it's not greater and we're assuming it's not equal, it's got to be less than, then we would just set t equal to the left and go back up to the top. But at some point we got to know if we're at the end, if we've just gone to the left or the right of a leaf node. So we need to do some extra stuff in here. So if our number is bigger than the current node's data, we have to do the following. If t right equals null, then set t right equal to whatever the new node is and return. And if our number is smaller than the current node's data, so that we're going to move to the left, before we move to the left, check to see if that left node exists. And if t left equals null, then change t left to be whatever our new node is and return. So it's a short loop starting at the root that does what we just did with finger and pen, right? Move down until, right, insert 25. So here's where t is. If our number is bigger than t data, well, it's not. If our number is less than t data, see if t left is null, it's not, so set t equal to t left. So now t is pointing to the 20. If our number is bigger than t data, or our number is 25, t data is 20, it is. See if the right node is null, it's not, so set t equal to t right. So now t is pointing at this node. If our number is greater than t data, which it's not, our number is less than t data, see if t left is null. In this case it is, so set t left equal to a new node containing our number and return. There's our new tree. There's one other edge case here. So what's the possible edge case that'll blow this up with a seg fault the way it's written? Say again? Close. Assuming they're not equal. The first thing I do is I check t.data, right? What if t doesn't exist? Right, so what if t is null? Because we don't have sentinel nodes with trees, so an empty tree, t is just going to be null. And if t is null, I can't look at its data piece because that'll seg fault. So if t is null, there's nothing in the tree yet. We're trying to insert some number. We should just return a new tree containing a single node, the root, which is our new node. So if t is null, we somehow want t to be a new node. But we got to be a little careful, because if we pass t like this, we can't change its value, because c is always passed by value. So this is the basic algorithm, okay, but the way we actually write this has to be a little different. And don't get too upset by this. So let's switch to actual C code here. So we've got our struct node, and it's got data, and it's got 2 pointers. So our insert function is going to take a struct node t, I'll call it root, and let's say an integer number. But if root is null, after we do this insert, root should be not null. It should be pointing to the one node in the tree, which is this new root that we've just created from number. And we can't change the value of this struct node pointer. So insert's going to actually return a struct node star. And we're going to declare it like that. So let me leave that as a function prototype. So what are we going to do in our main program? We're going to declare a variable in main that I'm just going to call root. You could call it tree or whatever you want. And we're going to initialize it to null. And I'm going to say start with an empty tree. Bless you. So in my main program, root is the name I'm using for my tree. And let's say I want to insert 10. Here's what I'm going to have to do. I'm going to have to say root equals insert root, comma 10. So I certainly want to pass my tree to my insert routine. I want to pass the thing I'm inserting. But whatever insert returns, that's going to be the new value for root. And that's absolutely necessary, because if root is null, insert should create a node containing a 10 with pointers to the left and right of null. And then it's going to return the address of that, and I'm going to say root equals whatever's at that address. And that's going to make my tree have one node, which is going to have a 10 in it. And then if I want to insert a 20, I'm going to do the same thing. But in fact, once I have a root, it's never going to change. So this root will end up being the same root that I pass in. That's okay. Does that make sense? Yeah.
So that would only work. So what if you pass in, for example, 5? Yeah. What if you were to pass in 5, because that would change the top one to 20?
No, the way that we're envisioning this insert function, so root is null, so there's nothing in the tree. So the first time we call insert 10, right, our code is going to say if t is null, then just return a new node. So after insert 10, root's going to look like this. Just going to have a 10 node. Okay, if we say insert 20, it's going to say is 20 bigger than 10? Yes. Is the right child of T null, yes, so it's going to create a new node, put it on the right. So now our tree is going to look like that, but root is still going to be this node.
So what happens when you're setting root equal to the insert function?
So every time after this, when we return, we're just going to return T. The same thing that we were given. The only time that this root's going to be different from that root is if the root we're passing in is null. And in that case, it's going to return the actual root of the new tree. But any time after that, whatever root we pass, we're going to get the same root back. But it does no harm to say root equals, right? But that's a consequence of the fact that the way we're doing our insert today, this is always going to be the root of the tree. That'll change eventually. We may insert something and the root may become some other node. And this will be useful in that case too. Did you have your hand up?
Yeah.
Yeah.
So how often do we change like our main root? So in all the examples we've seen, we've been given, like for instance, 40 is the typical one we've been using, is the main root, and everything else branches off of 40.
Yeah.
Is it ever the case where we will take that tree and then attach it to a root of another tree?
Yeah, in about 2 minutes.
Okay.
So that's a good question. All right, so reasonably okay with this for now. Take a root, return a possibly new root. Right, this is also going to happen when we delete. Right, so if we say delete, here's a tree and here's a number. If our tree looks like this, if it just has a single node 10 and we say let's delete 10 from the tree, T should end up being null after we're done. Right, before we do this, T is pointing to some node in memory. Well, if we free that node from memory, what should T point to? There's nothing there for it to point to anymore. So we're going to actually want T to be null to indicate the tree has no nodes. And we can't change this to be null because this is an argument passed by value. So when we delete, we would also say T equals delete. And we'd pass in the tree. And then in the case where we're deleting the root, this would return the new root, which would be null. All right, well, it wouldn't be 222 if we didn't do some recursion. So let's look at a recursive version of insert. So someone hands me this tree. I got my lazy hat on again. Someone hands me this tree and says, hey, I would like you to insert the number 88. And I don't feel like inserting anything anywhere. So what am I going to do? I'm going to look at 88. I'm going to compare it to the root. 88 is bigger, so I know 88 is going to get inserted somewhere in this tree. So I'm going to take this tree, hand it to a friend, and say, can you insert 88 into here for me? They'll do that. They'll hand me back a tree, and I'll just take the tree they give me, and I'll replace this whole right side with their tree, and I'm done. So to insert a number, see which side it goes on, left or the right, and if it goes on the right side, just ask someone to insert the number into that right subtree. Take the resulting tree and replace the original right subtree with a new one. And you're done. Because you know your friend somewhere put an 88 inside this tree in the right place, right? Probably right here. And so I take this and I replace this original tree with a new one that has 88, and I've put 88 into the original tree. So what does that look like? So struct node star insert. This is still going to be pseudocode, even though looks like I'm writing C. So if the number is bigger than root data, I'm just going to say root right. I'm sneaking in arrows. Root right equals insert root right number. Else my number must be smaller, so root left equals insert root left number. So if my number is bigger than the root, insert the number into that right subtree and replace my right subtree with that augmented tree. Otherwise, do the same thing on the left instead. So what's the edge case here? When does this blow up? When the root is null. So before we can say let's look at root's data or let's look at root's right subtree, we have to make sure the root isn't null. So if the root is null, what should we do? Make a new node. Whose value is whatever our number is, and then just return that new node. And that's the only work we ever actually do. If we're asked to insert into an empty tree, we create a node, we call malloc, right? We set the data portion equal to the number, we set the left and right portions equal to null, and we just return the address of that new node. Otherwise, we just defer to this magic function called insert and say insert over here or insert over there, take the result, glom it onto our tree, and return the final tree. So pretty cool. And that doesn't really come from thinking about this iterative algorithm, right? The iteration, we're really thinking about starting here and moving through, bouncing left, right as we work our way down the tree until we get to a leaf, and then tacking onto a leaf. To me, at least, this feels fundamentally different, right? This is really dividing the problem into one of two subproblems, either insert on that side or insert on this side, and then calling myself recursively to say do that insert and then sticking that into the original tree. So it's a kind of different mindset, but it's a pure recursive solution, and it's got some elegance to it. All right, let's talk about balance. So there's a binary search tree containing 10, 20, and 30. There's a different binary search tree also containing 10, 20, and 30. Here's a third binary search tree containing 10, 20, and 30. Actually, I think those may be the only 3 BSTs containing those 3 numbers. And this one, if we search for something, we may have to do 1, 2, 3 comparisons. If we're searching for 35, no, 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 out of nodes. This one, at most, we're going to have to do 2. And so this tree is somehow better. It's going to take fewer operations on average to do something we want to do. And so there's a notion called balance. And the more balanced a tree is, the shorter and wider and more filled in it is. So right, there's a tree containing those 7 nodes. Here's the tree you keep seeing. Maximum number of operations to search this tree, 1, 2, 3, 4, 5, 6. This tree, 1, 2, 3. So this will turn out to be a balanced tree. This will turn out to be definitely not a balanced tree. And eventually, a couple of weeks, we're going to talk about how to make trees look more like this instead of like that. Because if a tree's balanced, it's going to work better. If it's grossly unbalanced, it's really just a glorified linked list. And we're back to order n, search performance. So we like our trees to be balanced. And we're going to talk about how to do that. And the main trick is going to be every time we insert or remove something, we may need to make an adjustment. An empty tree is balanced, and a tree with a single node is balanced, and actually a tree with just 2 nodes is balanced. But once we add a 3rd node, if we look like this, we're going to do a transformation to turn this into that. And it'll turn out every time we add 1 node to a balanced tree, it may become unbalanced, but not too badly. Just a little bit in such a way that we can do a minor tweak and rebalance it. So before we can do that, we need to know, is a tree balanced? What does it mean? What's the actual definition? And we can look at a tree and usually tell, you know, this looks nice and symmetric and wide and fluffy, and this doesn't, right? But let's look at a definition for balanced. So I'll switch to root today. So we're going to pass the root of a tree, and we want to know if the tree is balanced or not. And let's return 1 if the tree is balanced, 0 if it's not. Well, the definition of a balanced tree is the following. I'll start using arrows. So the height of the left and right subtrees have to be within 1 of each other. They don't have to have exactly the same height. But the left and right subtrees, the heights can't differ by more than 1. So absolute value of the height of the left minus the height of the right must be less than or equal to 1. So that's one requirement. And the left subtree has to be balanced. And the right subtree has to be balanced. So if all 3 of those things are true, the tree is balanced. So left and right subtrees heights are within 1. Left subtree is balanced, the right subtree is balanced. All 3 are true, the tree is balanced. And so the definition is recursive, so our balanced function is going to have to call balanced on subtrees. And what's our usual edge case that we haven't dealt with yet? When it's null. So if the root is null, or if all of this stuff is true, return 1. Otherwise, it's not balanced. So our whole balance function is going to be basically, it can be one return statement. Yeah.
So visually, what's going to happen is we're going to take roots from the right or left and then attach them to the right or left side.
Yeah. To balance, you mean?
Yeah, to balance them.
Yeah, so what's really going to happen is what we call rotations. So let's say we're inserting 10, 20, 30. So we'll put in a 10. We'll put in a 20, it's got to go to the right. We'll put in a 30, it's got to go to the right. We're going to calculate what's called a balance factor, which will tell us how unbalanced each point of the tree is. And we'll find a balance factor that's different from 1, -1, or 0. And then we're going to do what's called a rotation about this point, which means if this is what our tree looks like now, we're going to turn it into this. So we're going to bring that 10 down, put the 20 up and the 30 down. And if there's other stuff hanging off of here, it just kind of goes along for the ride. And there's going to be 4 kinds of rotations we have to do, and it'll depend on an analysis of our balance factors. So we'll talk about that algorithm in detail, and I may have you code it up, because it's something you should do once in your life, which is how many times I've done it. So balance is another one of these things that has kind of a naturally recursive definition. Yeah?
So is balance mostly about restricting or trying to minimize the height of the tree?
Mm-hmm, exactly.
So it doesn't necessarily have anything to do with how the data is organized within, so long as the height is minimized.
Yeah, we're really just trying to minimize the height. Because the height tells you what the maximum search time would be. Right? Height is the depth of the deepest node. So if you search for the deepest node, or search for something that's not in there but is along that path, it's going to take you however many steps corresponds to the height.
But other than that, we don't care about how it's organized within that height.
As long as it's still a binary search tree. Smaller on the left, larger on the right, correct. I shouldn't say we don't care. We may care. I don't know. I haven't thought about it in those terms. There's a specific algorithm we're going to use to restore balance. And I don't know if any other algorithm that minimizes the height would necessarily work as well. But ultimately the goal is to end up with a tree with the smallest height possible.
Okay, but it doesn't matter if like you have more branches off of like your rightmost node or like your centermost node or anything like that.
No. In fact, in general, the trees are not going to look nice and you know, beautiful like this. Right? That's only going to happen if you have a number of nodes that's 1 less than a power of 2. So usually there's going to be some extra stuff hanging somewhere. All right, well, let's tackle deletion. So there's an arbitrary tree, and we want to delete a node. And if we wanted to delete the 12, that's easy. Just change it to null. Same with the 73 or the 77 or the 32. Deleting a leaf is pretty straightforward. Just erase it, right? Change the thing that's pointing to it to be null. What's the worst node to try to delete in here? Probably the root, right? 40. because it's got children on both sides, and we can't just free this node because now we're going to orphan 2 entire lineages. So deleting the root is kind of fundamentally a special case. If we're deleting anything other than the root, we can ask a friend to help. Let's say we want to delete 75. Yeah, go ahead.
Won't we always be deleting the root, per se?
Well, what if I want to delete 75?
Well, we would pass it along to a friend until 75 was the root.
Right. So eventually somebody's going to have to delete the root. So let's look at the bigger recursion picture. Suppose I want to delete 75. Right, I compare 75 to 40. It's not the root. Whew, I don't have to worry about that, right? 75 is bigger. I know it's going to get deleted from this tree. So I hand this tree to a friend. I say, can you get rid of 75 for me? They hand me back some kind of new tree that looks like this with 75 removed, and I just replace this with the tree they give me back, and I'm done. So we're going to write a recursive function again, and as long as we're not deleting the root, we don't have to do any work. We just call delete on one of the subtrees and then replace the subtree with that modified tree. So the whole trick's going to come down to how do we delete the root. So let's spec a little bit of pseudocode. And I'm just going to assume that we know the node is in the tree. So before you call delete, call search, or in the top of delete, call search, or something, right? So I'm not going to worry about what happens if the node's not in there. So if num is less than root data, then root left equals delete root left comma data, or num. And I'm just going to return the root. So if we're trying to delete, let's say 10, right? 10 is smaller than 40. I'm going to call delete on this left subtree. I'm going to say delete 10 from here. Something will happen to make 10 go away and everything still works like a tree. And I'll get back the root of this tree from delete, and I'll set my root left to point to that modified tree, and I'll just return this root. So same thing on the right. If the number is greater than root data, modify the right subtree. And return the root. Otherwise, we got to do the work. We got to remove the root. The root cannot be null because I'm making this assumption that it actually contains the node we're trying to delete. So I know that the root's not null. So I don't have to worry about that edge case. But there could be a case where the tree consists of a single node, which is the root we're trying to delete. Or it could be something like this, where we're trying to delete 40, and there's stuff we have to deal with. So any thoughts how to get rid of that 40 and keep this thing looking like a tree? Yeah. Okay, we're going to need a new root. What would be a good root? 60? So yes, in this case, we could put the 60 up here and we'd be done. But what if we've got a 55 hanging over here?
So good.
So I could put a 60 here, but then where's the 55 going to go if I'm going to make 20 the left child?
Could you then call like the insert function and reinsert 55?
We could, but if we've got this, then that's going to get messy. These are cool ideas, though. It'd be fun to implement these. Yeah.
Could you just find the rightmost node and then
Ah.
attach the 60 to that?
That sounds cool. So find the rightmost node. So that's basically what we're going to do. So let me phrase it a little differently. There's two ways we can do this. They're symmetric. Suppose we find the largest number in this left subtree. The largest number in this subtree is bigger than everything else in this subtree and smaller than everything in this subtree. That's an excellent candidate for the root. Because whatever we put up here has to have the quantity, the characteristic that everything over here is smaller, everything over here is greater. So if we pick the largest number from here and we move that to the root, we should have a good binary search tree. Equivalently, we could pick the smallest number from the right subtree and move that up to the root. Okay, there's some details. All right, so I want to delete the 40. We're going to get rid of that. We're going to take the largest thing from the left subtree and move that up. Here's our new tree. Okay, that works great. We're not worried about balance this week. So as long as it's still a BST, we're happy. What if our tree looks like this? The largest thing in the left subtree is 30. So we're going to move that up to the root. But 30 had something on its left. In fact, it might have had a bunch of things on its left. And if we just move 30 up and it adopts this subtree on its left, these become orphaned. But what can we do with these nodes so they don't disappear from the tree?
Assign it to me.
Yeah, so we can just replace the 30 with whatever it had on its left.
We just take only left side.
For this case, we're only doing the left side. We could also do the same thing on the right instead. We could take the smallest thing from the right.
Would that be determined by the balance of the tree?
That would be one way. Or you could just alternate every time that you delete to hopefully keep it balanced-ish.
And there will never be anything less than 20 to the left of 30 because of how we're inserting.
This is true. And there will never be anything to the right of 30, because if there was, it would be bigger than 30, and 30 wouldn't be the biggest thing in that subtree. So we're guaranteed, if this is the largest thing in the left subtree, that its right child is null. So at most it has a left child, and we can have that left child be adopted by whoever was the parent of 30. Yeah.
Also, can we just directly use 10 as the first, assign 25 to 20? Make a 20 to 25?
Say that again?
So I could replace, use a 10 as a head, and link 25 and the four rest of those with 20.
Where would the 25 go?
20 goes to 25.
20 and 25, I think so.
I mean the left side.
20 over here?
Yeah, if we get 10 become the header.
If 10 goes here, 20 can't go there.
Can go smaller side.
It's got to be smaller on the left and bigger on the right. There are other ways we can do this, right? For a particular tree, there's going to be different ways we could
So we can
do a
have
deletion.
left and right, so it will always be left smaller, right larger.
Yeah, left has to be always smaller, right has to be larger. Okay, so let's write down these steps. So delete the root. So we're going to have a struct node star. I'm just going to call it largest. We're going to set that equal to the largest node on the left. We have to do that, but we can do that by just traveling down and going as far to the right as possible. So assume we've got some way to set largest, a struct node star, equal to the largest node on the left. So here's our root. There's other stuff going on here. This is largest. So previous is going to be the node right before we got to the largest node, the parent of the largest node. And we have to do some work to set these things to point to the right nodes, but that's not too bad. And then what do we want to do? We want to take largest and move that up to the root, and we want to take largest left child and move that to be the right child of previous. And it's just like it would sound in words. Previous right equals largest left. Largest left equals root left. Largest right equals root right. And free your root. And then return the new root of the tree, which is largest. Yeah?
Wouldn't the largest node in the left subtree always be, in that case, always be the one immediately to the left of the root?
No. Oh, yeah, so this is a bogus drawing. So, yeah, pretend that node's not there. So anything off to the right is going to be larger, and it could be, right, something like this. So this might be the largest, and this would be the previous. So, but yeah, if the node to the left doesn't have a right child, then that's the largest node, you're right. All right, so we'll go through this more carefully when we're talking about PA4. But the punchline here is that you figure out what you want to do to the nodes, you write a few lines of code to mimic that in C. All right, so I will see you tomorrow for the midterm.